What if quantum entanglement isn't limited to tiny particles hidden away in laboratories? For decades, physicists believed that the most remarkable quantum effects could only be observed in extremely small systems, individual atoms, molecules, or photons carefully isolated from the surrounding world. But a new experiment has revealed something extraordinary. Scientists have detected strong quantum entanglement inside a crystal large enough to hold in the palm of your hand, opening a new window into the hidden quantum nature of matter itself.
Quantum mechanics describes a world that behaves very differently from our everyday experience. At the quantum scale, particles can exist in superpositions, occupying multiple possible states simultaneously until a measurement is made. Even more strangely, particles can become entangled, forming connections so deep that they can no longer be fully described as separate objects. For more than a century, these bizarre properties have challenged our intuition and transformed our understanding of reality. The question of whether quantum phenomena can apply to large objects is almost as old as quantum theory itself. In 1935, physicist Erwin Schrödinger proposed his famous thought experiment involving a cat inside a sealed box. According to a literal interpretation of quantum mechanics, the cat could exist in a combination of both alive and dead states until observed. The idea was never meant to be taken literally. Instead, it highlighted a profound mystery. Where exactly does the quantum world end and the classical world begin? Scientists have spent decades pushing the boundaries of quantum behavior into larger and larger systems. But what happens when we move far beyond individual atoms? Can a macroscopic object containing countless particles still exhibit genuine quantum properties? Can quantum entanglement survive inside materials visible to the naked eye? These questions motivated the research that would lead to an unexpected discovery. Researchers at TUW Wien approached the problem from a different perspective. Instead of attempting to place an entire crystal into a quantum superposition, they asked a simpler question. Are the crystal's constituents collectively entangled? Professor Silke Bühler-Paschen compares the situation not to Schrödinger's cat, but to an anthill. When an anthill is disturbed, it is not a single ant that responds. The entire colony reacts collectively. The scientists wanted to know whether something similar might be happening among the quantum particles inside a strange metal. To answer that question, the researchers relied on a powerful concept from quantum information theory, known as quantum Fisher information. The theoretical framework was developed by Peter Zoller and his collaborators. Quantum Fisher information measures how sensitively a quantum system responds to external changes. If particles behave independently, the response remains limited. But when particles are entangled, the entire system can react collectively, producing a much stronger response than expected. By measuring this enhanced sensitivity, scientists can directly estimate the amount of quantum entanglement present. The material chosen for the experiment was a strange metal crystal composed of cerium, palladium, and silicon. Although only about a centimeter in size, this crystal contains an unimaginably large number of interacting particles. For years, strange metals have fascinated physicists because they exhibit behaviors that cannot be fully explained using conventional theories. The crystal would become the perfect testing ground for exploring large-scale quantum entanglement. Strange metals occupy a special place in condensed matter physics. Unlike ordinary metals, their electrical properties often defy traditional theoretical models.
Many strange metals display unusual transport behavior, strong electronic correlations, and connections to high-temperature superconductivity. Despite decades of research, many of their most fundamental properties remain mysterious. Understanding their quantum nature has become one of the major challenges of modern physics. To probe the crystal, the team traveled to the Institut La Langevin in Grenoble, France. There, doctoral researcher Federico Mazza directed beams of neutrons into the strange metal. Neutrons are ideal probes because they can penetrate deeply into materials and reveal how their microscopic constituents respond to disturbances. The experiment carefully measured how energy transferred between the incoming neutrons and the crystal itself. The results revealed something remarkable. In a conventional material, a neutron would be expected to interact primarily with an individual particle, but that is not what the data showed. When the researchers analyzed the measurements using quantum Fisher information, they found evidence of collective quantum behavior that could not be explained by independent particles. Something much larger was happening beneath the surface. The analysis revealed direct evidence of strong multipartite quantum entanglement. Rather than interacting with a single isolated particle, the neutron appeared to trigger the coordinated response of groups containing at least 9 quantum entangled entities. This means that multiple particles were acting together as a unified quantum system. For a macroscopic solid object, this level of collective quantum behavior is extraordinary. The crystal was not behaving as a collection of separate components. Instead, parts of it were functioning as a deeply connected quantum network. The discovery represents much more than a curiosity. Quantum entanglement is considered one of the most valuable resources in quantum science. It plays a central role in quantum computing, quantum communication, and quantum sensing. Demonstrating strong entanglement inside a large solid material opens new opportunities for studying quantum phenomena in realistic physical systems. It also provides a powerful new tool for investigating complex materials. The discovery may also help explain another puzzling observation. In 2025, researchers from TU Vienna and Rice University reported that electrical current flows through strange metals in an unusually quiet manner. Compared with ordinary conductors, these materials exhibit surprisingly low levels of electrical noise. The newly observed entanglement offers a possible explanation. Rather than behaving independently, the particles may be coordinating their motion collectively, suppressing fluctuations and producing smoother electrical transport. One of the most exciting aspects of the work is the connection it creates between two major scientific disciplines. On one side stands solid-state physics, focused on understanding the properties of materials. On the other stands quantum information science, which studies entanglement, quantum resources, and information processing. This experiment demonstrates that concepts developed for quantum technologies can provide entirely new insights into the behavior of complex materials. A bridge has been built between these fields, allowing ideas to flow in both directions. Researchers are already looking ahead. If entanglement can be identified and controlled within strange metals, these materials could one day contribute to future quantum technologies. Possible applications include ultra-sensitive measurements, advanced quantum sensors, and new approaches to quantum metrology. The goal is not only to use quantum information theory to understand materials, it is also to explore whether unusual materials can become useful tools for the next generation of quantum devices. For more than a century, quantum mechanics has challenged our understanding of reality. Now, scientists have shown that one of its most extraordinary features,
quantum entanglement can be directly observed inside a macroscopic crystal visible to the naked eye. The experiment suggests that beneath the familiar world around us lies a hidden layer of collective quantum order, a world where particles do not always act alone, a world where matter itself can become interconnected in ways that classical physics never imagined, and perhaps a world that is far more quantum than we ever thought possible.